Alright, y'all, so hopefully you picked up the notes, and we're going to talk about 6.3, which is binomial radical expressions. We're actually going to basically talk about how you add and subtract radical expressions. As you can tell, I'm still pretty sick, so hopefully that you can decipher what I'm saying regardless. So when it comes to adding and subtracting radicals, it's very similar to what we talked about with multiplying, except we have to take it a step further. So when we add or subtract radicals, they have to not only have the same index, but they also have to have the exact same radicand. Okay? So big keys here are index and radicand. These can be combined simply by using the properties of real numbers. So, if you will, look at this chart here with me. Okay? I have the square root of 2 plus 3 square roots of 2. So that gives me a total of 4 square roots of 2. You could see that if it makes you feel more comfortable, you can put a 1 up front there. So you can see where that 4 square roots of 2 comes from. If you have, on the next one, we have square root of 5xy plus 8 square roots of 5xy. That means in total I have 9 square roots of 5xy. So you can almost treat what's in that radical as its own variable and then just combine how many of those you have all together. So when we talk about subtracting, it's the exact same way. I have the cube root of 7 minus 5 cube roots of 7. That gives me a negative 4 cube roots of 7. Okay, so underneath there, you can see on the sum and difference formulas down here, they used a GCF essentially, but most of the time we don't see that. We'll just use combining like terms. Okay, so let's take a look at these 3 examples here. On the first one, I need to ask myself, is my index the same? And is my radicand the same? So I can see I'm taking square root here, and the 5x is underneath both of those radicals. So I can go ahead and simplify this. If I have 3 square roots of 5x minus 2 square roots of 5x, what's 3 minus 2? 1. So I have 1 square roots of 5x. Do I really need that 1 there, though? No, not necessarily, so I can just write this as the square root of 5x. Okay, that's my final answer. All right, let's take a look at B here. On B, I need to ask myself the exact same questions. Is my index the same? The index number is the same here, but what do you notice with those radicands? I have a 7 and I have a 5. Those are not the exact same, so this is not possible. Okay? When those index numbers and those radicands are not the same, I cannot add or subtract like terms. Okay? So I will leave you to do C on your own. As you notice on C, you should see that the radicands are the exact same, but something that sticks out here is my index number. Those are not the same, so again, this is not possible. Okay. In order to add or subtract, the index and the radicand have to be the exact same. Okay. On this next slide, we're going to throw in some subtracting. Okay. If you can, go ahead and do these entire problems on your own. You are more than welcome to check with a neighbor to see if you are on the right track. And you can also follow along with me if you need to. So on the first problem, As always, we identify, is our radicand the same? Is our index the same? My indexes are not the same here. So this is not possible. On B, same steps here. I got to check my index and I got to check my radicands. I see that we're taking the square roots of both of those, so my indexes are the same. And then under my radicals, I have the exact same thing. So I'm good to go. I can combine my outside numbers. I have 3x square root of xy plus 4x square root of xy. That gives me a total of 7x square root of xy. Okay. All I had to do was add those outside numbers to give me a total of that 7x square root of xy. On C here, again, let's look at our index and our radicand. Are those the exact same? Are they identical? Yeah, they are. So all I need to do is subtract the 17 and the 15. 17 minus 15 gives me 2 fifth root of 3x squared. I still have my index and my radicand as the same. I just simplified down. If you have questions, ask a neighbor or save them for tomorrow. Okay. All right. So some of us have taken geometry, so we're going to apply this to a real-world type of problem. It says in the stained glass window design, the side of each small square is 5 inches. It says find the perimeter of the window to the nearest tenth of an inch. Ooh, this one's a tricky one, okay? If you have a square, okay, and each side is 5. Okay. We can use our geometry skills and identify that this is a 45, 45, 90. And so in order to find this diagonal length, all I have to do is take my side and multiply it by the square root of 2. Okay? So that means this distance up here is 5 square roots of 2. This right here is another 5 square roots of 2. This is another 5 square roots of 2. And I also have that on the sides. So every length that I see here is 5 square roots of 2. So if I'm talking about perimeter, okay, if I'm talking about perimeter, that means I have to add up all the sides in my figure. Okay? Well, how many 5 square roots of 2 do we have in this figure? Let's count them. I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I have 10 5 square roots of 2. Instead of going there and adding every single one of these up, I know they have the same index and I know they have the same radicand, so I can make my life a lot easier and use some multiplication. So my final answer for my perimeter is 50 square roots of 2 inches. Okay. I know a lot of us haven't taken geometry yet, so you're figuring it like, Miss Ellis, where is this coming from? But it's really, really, really okay. Don't stress much about it. We can talk more about it in class. I just wanted to show you how geometry fits into Algebra 2 and how we can use this in a real-world application. Okay. All right. So this is where we use our laws of simplifying radicals in order to be able to add higher order radicals. So on this problem, it says when you have the sum or difference of radical expressions, you must first simplify each expression and then combine like expressions, okay? So we've been talking about this. I can break down each one of these as simple as I possibly can. That way, I can see how they add together. So if I have the square root of 12, the square root of 12 breaks down into the square root of 4 times the square root of 3. Well, what's the square root of 4? 2. So I should have 2 square roots of 3 as my most simplified answer here for square root of 12. So now let's break down the 75. What perfect square factor goes into 75? We can look at our list on the board, and we should see that it's 25 and 3. Well, the square root of 25 is 5 square roots of 3. And I can see here that I'm starting to get a trend here. Ooh, square root of 3, square root of 3. So if I'm going to add all of these up, I should probably have the exact same radicand. And then can I simplify the radical 3 any further? I don't think so. It's already simplified down. So this was a plus in between here, and then minus square roots of 3. Well, what's 2 square roots of 3 and 5 square roots of 3? 2 and 5 gives me 7, and then minus, can I say there's a 1 sitting right here? Yeah, I could do that. So 2 plus 5 gives me 7, and then I subtract 1, so this totals to 6 square roots of 3. The only thing you have to do here is simplify down every radical till it is in its simplest form, and then we can combine like expressions like we saw in the first half of this lesson. Okay, let's look at the second question, because the second question, I'm not dealing with square roots, I'm dealing with cube roots now. So I'm going to simplify the cube root of 250. And what's the perfect square factor that goes into 250? That's kind of a tricky one, right? But I think I can figure it out. That should break down into the cube root of 125 times the cube root of 2. Okay? Because 125 times 2 gives me the 250. Okay? Cube root of 125 is 5. So I'm left with 5 cube roots of 2, okay? Let's break down the cube root of 54. We saw this yesterday in class. The cube root of 54, the perfect cube factor that goes into that is 27, and I still have my cube root of 2. The cube root of 27 is 3, so I have 3 cube roots of 2. And on my last term here, the perfect cube factor that goes into 16, we can look at our list. That should be 8, and I'm left with cube roots of 2. Okay. Cube root of 8 is 2, and I'm left with the cube root of 2. And all I have to do is fill in my signs here. So I have a plus in between there, and a minus in between there. And I notice here, all of my index and my radicals are the exact same, so I can simplify this down. I have 5 plus 3 gives me 8 minus 2. That gives me 6 cube roots of 2. Okay. This is why yesterday it was so crucial that we discovered how we simplified radicals based off of square roots and cube roots. Okay. I will leave you to do the last one on your own. All right, so now that we've talked about adding and subtracting, we're going to talk about how you FOIL with radicals, okay? And you actually saw this when we did complex numbers back in Module 4, so this isn't too terribly new, but I do want to hit this again before we move any further. So when I want to find the product of these two numbers here, okay, all I have to do is think of the saying, out without, in within, okay? You are literally going to multiply what is on the outside together and what is on the inside together, okay? So let's think about this. It says here that you can use the FOIL method or the box method to multiply binomials that have radical expressions. So this is why we are doing this step first, okay? So when we multiply here, I can do out without and in within. So my 2 and my 4 are on the outside here, okay? So I'm going to multiply those two terms together. So I have 8. And then I multiply the insides with the insides, okay? I multiply what's under the radical with the other part that's under the radical. I have the square root of 2 times the square root of 2, which gives me the square root of 4. And I can take the square root of 4, so this gives me 8 times 2, which is equal to 16, okay? Remember that saying. I'm going to write it out up here. Out without, in within. Okay? You multiply what's on the outside of the radical with the outside. You multiply what's on the inside of the radical with the inside. All right. So let's take a look at some problems here. On A, we know how to FOIL, okay? Remember FOIL, first, outer, inner, last. So I'm going to do all of these steps while keeping in mind my out without and the in within, okay? So here I go. My first is 4 times 5, which gives me 20. My outside, I have 4 times 4 square roots of 2. Now here, remember, out without, in within. Does this 4 have a radical with it? No. So I only multiply the 4 by the number that's on the outside, which is a 4. So I have plus 16. Do I have another radical to multiply with the far radical? No, I don't. So all I have there is that square root of 2. Okay. When I do my inner here, okay, out without, in within, I have a 2 and a 5 on the outside, which gives me 10. And then I have left just a radical 2. And then the last here, I have the 2 square roots of 2 times 4 square roots of 2. Well, that's what we just did on that last problem. So I have out without, which is 8, in within. The square root of 2 times the square root of 2 gives me the square root of 4. But from here, we can simplify this down. I have 20 plus 16 square roots of 2 plus 10 square roots of 2. And then my last term here, I can take the square root of 4, which is 2. So I have 8 times 2, which is 16. Now, I'm almost finished. All I have to do is combine like terms here. So I can combine the 20 and the 16, which gives me 36. And I can combine the 16 square roots of 2 with the 10 square roots of 2 to get 26 square roots of 2. All you have to keep in mind here is that out without and the in within. Okay, let's look at B here. Keeping my FOIL method in mind, I'm going to multiply 3 times 5, which gives me 15. My outside, 3 times the square root of 7, gives me 3 square roots of 7. My inside here is the square root of 7, negative square roots of 7, times 5 gives me negative 5 square roots of 7. And then my last here, the negative square root of 7 times positive 7 gives me negative square root of 49. And I should be able to simplify that down. So I have 15. And I'm going to go ahead and combine these two because they're the exact same. 3 minus 5 gives me negative 2 square roots of 7. And then my last term here is minus the square root of 49 is 7. So let's simplify this even further. 15 minus 7 gives me 8 minus 2 square roots of 7. Okay. Take a second and see if you can do the last one on your own. All right, you can look up here on that last one. I just FOILed that out, and I combined my like terms. I got 46 plus 16 square roots of 5. All right, we're in the home stretch here. We're going to talk about conjugates. When we do conjugates, we saw this when we talked about simplifying radicals and complex numbers. Remember, the conjugate is just the opposite sign in the middle, okay? All you have to do is multiply by that opposite sign. So on problem 5 here, we see that we have 5 minus the square root of 7 and 5 plus the square root of 7. And the reason why we talk about these conjugates is because something really special happens when we FOIL these out. So you can see here, I have 5 times 5, which is 25. That's my first. My outer is plus 5 square roots of 7. My inner is negative 5 square roots of 7. And then my last term here gives me negative square root of 49. Now, this is the whole part about why conjugates are so special. Because what do you notice there happens in the middle? It cancels out, right? So my 5 square roots of 7 minus 5 square roots of 7 goes away. And I am left with no radical really to tend to. Because what is the square root of what's the square root of 49? Right, 7. So as long as I have my minus sign there, I can simplify this down. 25 minus 7 gives me 18. Okay. So with conjugates, I get a real rational number. Okay? That's why these are worth noting here. And as some of you might be able to see, as a shortcut, instead of having to FOIL every single time, you can just square the first term and then square the last term. So you'll notice that that radical goes away and then you just subtract the two. So that's something worth mentioning there if you can note that as well. So let's talk about A here. 6 times 6 gives me 36. My outer and my inner cancel, So I'm just going to look at my last term here, which gives me minus the square root of 144. The square root of 144 is 12. So my final answer is 24. Take a second and see if you can do the last one on your own. You can look up here. I got 1 as my final answer. I squared the first term, squared the last term, or multiplied the last two to get the square root of 64. Square root of 64 is 8. 9 minus 8 gives me 1. Okay. This is just taking what we did on that last slide and adding a little bit more to it, throwing in that term conjugate. Okay. And the reason we use the conjugate is because I have to see how I get rid of those radicals on the bottom of my fraction. So anytime we see that radical in the bottom, we have to multiply by the conjugate. So here I multiply, I multiply by my conjugate. If I have the square root of 5 minus square root of 2, I'm going to have the square root of 5 plus the square root of 2, and I have to multiply by that on top and bottom. Okay. And then from here, this just became a multiplication game, really. I multiply across the top. Okay. Remember, out with out, in with in. Okay. So you should have 3 square roots of 10, because I just distribute here. Okay. And then plus 3 square roots of 4. And this is all over. I'm going to multiply my conjugates together. And as you should see, if I multiply these together, I get the square root of 25 minus the square root of 4. That gives me 5 minus 2, which gives me 3. Okay. So as we can see on the top, we might need to do a little bit of simplifying. This is 3 square roots of 10 plus the square root of 4 is 2. So 3 times 2 gives me 6 all over 3. And possibly on the final, you might see this simplified. You could see this as the square root of 10 plus 2 because the 3's cancel out, and what's 6 divided by 3? 2. Okay. So let's get that written down, and then we'll move on in just a second. All right, let's look at another one. Let's let this sink in for a second. If I have the square root of 3 minus the square root of 5, the conjugate is the square root of 3 plus the square root of 5, and I need to do that on top as on bottom. Okay. So again, from here, I just multiply straight across. And I'm going to make sure I distribute where I need to. So on the top, I should have 2 square roots of 21 plus 2 square roots of 35 all over. All I need to do is FOIL down here. This gives me the square root of 9 minus the square root of 25. And let's simplify this. I don't think I can simplify anything on the top, so let's leave that alone, okay? They don't have any common perfect square factor that goes into them, so I can just leave those alone. And then I have 3 minus 5, which gives me negative 2. I can see here that I have a Dorito. We talked about that before. So I can take out a 2, or let's say a negative 2 on every single one of these terms. So this ends up giving me negative square roots of 21 minus the square root of 35. And I am finished. Okay. Let's save B for tomorrow, and we'll open up class with that problem. Okay. So the last slide is a do you know how, but we're going to skip that for now, and we're going to go straight into the 6.3 worksheet. I will have designated problems for you to do on that worksheet that you will work on the rest of class, and then you also have the 6.3 book work. I hope you all really enjoyed this. I'm glad you showed up. I'm sorry I couldn't be here, but hopefully this helps you learn some material today. I will see you all tomorrow. If you have any questions, I am staying after school today, and I will be here for you with any questions that you have. I'll see you later.